now a new generation that will have made sense of these things using different papers. Okay. Is Tristan here? Tristan's here. Yeah. Okay. Thanks, everybody. So it's my pleasure. Okay, we're gonna get started. Hopefully everybody has some cookies to tide you over. So happy summer Wednesday, everyone. Good to see all of you here. It's my pleasure to introduce Vijit Maithel for his thesis defense. Vijit first came to my attention some number of years ago. He was working on moist static energy budgets in the Indian monsoon, and in particular kind of simple idealized models that make some very strict assumptions about the moist static energy budget that aren't necessarily always true, although they've proved useful. And so I was able to convince him to look at moist static energy budgets in more kind of an observational rather than just theoretical framework. And this led to him kind of expanding on the moist static energy budget framework to come up with a phase plane perspective of the energetics of large-scale tropical convection. So a phase plane-based perspective of the energetics is based on moist static energy budgets, but it's kind of an expansion beyond that. That maybe some of you have seen a little bit of, because my student Cooney and I developed that, I guess probably something like 10 years ago now. But maybe not quite. 2016, I guess, is the paper. No, 2015 is the paper. 2015 is the paper. So yeah, we developed it probably something like 2014. So yeah, almost 10 years. But Vijit has really been able to take this perspective and show some of the power of what it can do that I wasn't even aware of at all. So he's kind of combined this with dynamical systems reasoning that he came in to the program with to use these phase planes to reason about how different dynamical systems are behaving and apply some methodologies to that to kind of explore some of the questions that were left unopened back in 2015 or whatever, 2017. So he has a published paper on that, so he's not going to focus on that too much, but I did want to call that out as some really nice work that Vijit really drove forward. And then more recently, he's been working on and mostly I want to let you tell them about it, so I'm not going to talk too much longer. But more recently, he's been working on thinking about convective aggregation in observations, and has come up with some really unique ways of studying this, and that he's going to tell us about that maybe are even more insightful than these phase plane-based moist static energy budget things, at least for certain questions. Questions related to kind of why the atmosphere is aggregated the amount it is, why it changes aggregation in the ways that it does, things like that. So, and there's a big active community working on aggregation that has mostly looked at idealized models or very limited region observations. And so this, I think, makes a really nice complement to that existing work, and we're hoping it'll be of interest to a lot of people. So, yeah. Okay, with that, I'll stop talking and let the man of the hour talk.
Thank you, everyone. Hello. Yeah, is this too loud? No, perfect. And I hope everyone on Zoom can also hear okay. If there are any issues, just put it in chat. We can address those here. But yeah, thank you everyone for tuning in today for my PhD defense talk. I'll be, as Larissa very nicely motivated it, so I don't have to do any of that. I'll skip right to the results. but no, I will do that. But yeah, I'll talk today about this phase plane framework and different diagnostic metrics that we have built based on that to look at evolution of moist static energy budgets for tropical convection. And so the talk today would go something like this. I'll start off with giving a broad motivation and introduction to talk about what we mean or what we are visualizing when we say large-scale tropical convection. What are the physical constraints that kind of form like the physical basis for building this entire framework on and act as constraints within which we are bound in this framework. I'll introduce the particular metrics in diagnostics. We're using MSc budget, the phase plane, and the life cycles that we will look at. Then I'll introduce what are the key aspects that we address in this study. And then for the main section of this talk today with the results, I can broadly divide it into like a part A and part B, where one part is looking at these moisture recharge discharge cycles, and part B is looking at aggregation disaggregation cycles. As Larissa mentioned, I'll give only like a brief overview for part A and present more about the results from part B. So thinking about the tropics, which depending on which definition you like to use, can be thought of as the region within this red box, most of it covered by ocean, but there's also some land in there, and that land has 40% of the world population. So it is important. And as I was thinking about why are tropics important, I had way too many ideas. I did not know how to say that concisely, so I did what everyone does today. I used ChatGPT. And it says the study of tropical weather is crucial for safeguarding lives, protecting ecosystems, ensuring food security, and advancing our understanding of climate dynamics, leading to more informed decision making across various sectors. And that is surely true. A large population lives in these regions affected directly by the extreme weather in this area, including tropical cyclones, tropical waves, extreme precipitation events. A lot of agriculture in the region is dependent on the rain received through rainfall and the different seasons in the tropics, and so it is directly relevant for food security. And perhaps what is of most interest to me is its importance for understanding climate dynamics in general. Apart from just understanding tropical climate, it is also important for understanding climate patterns in areas outside the tropics through teleconnection patterns which are driven and based on the tropics. So with that in mind, we'll start looking at convection in the tropics. And I guess for the focus of this talk, it is nice to think of convection in the tropics as like these two broad classifications, where one is like a small scale and one is large scale. Small scale looks something more at cloud scale or mesoscale, something which is confined within like one grid box of your global climate or numerical model. And you're basically thinking out of the different clouds that you see, which clouds develop into deep convection, which do not, how high do they go, how long would they last, and things like that. But then there is another perspective, which is the large scale feature, which is basically like a combination of a bunch of these small scale features. And we see a lot of large scale convective variability in the tropics, shown here through this intertropical convergence zone, which is probably like the largest feature, which is like this narrow zonal band of convection that we see exist almost at all times in the tropics in various stages of activity, and this band can move up or down. Tropical cyclones are another large-scale feature which are very, very, very important because they are extreme precipitation event and cause a lot of damage and affect human lives. And other modes of large-scale variability which are more directly relevant to what we look at today are, in general, these convectively coupled modes, which can be visualized through this animation from Professor Adame's website, where we can have different wave-like features, different cyclic features at different scales. They move at different speeds. They move east, they move west. But But these are all large scale features which have basically like these small scale features embedded within them and exhibit some type of organization at these large scales. And so if we want to understand tropical convection, what we want to understand or what we need to understand is how all these scales connect with each other and what variability that gives rise to. And to do that, we have to understand how convection is interacting with its environment. Basically, in our models, you can think of them as small boxes, and the models solve for what happens within one box, and then you have all these boxes stacked together besides each other. And depending on what type of model you are, they could be doing things differently, but basically, they'll be working at these small scales at a box. They'll tell you, okay, I have this much cloud in this box, this much cloud here, and that should translate into what happens at the large scale, where if I take a bigger box encompassing multiple grid boxes, that tells me, okay, where convection is happening, how strong it is, how it is evolving. So these small scale things should add up. But as it turns out, why we are here, why I have a job, is because models are not able to do that all the time. Or they do not do it most accurately. And that is where observations can come in. Observations, especially at the large scales, can help us identify the constraints within which models should work and help us understand what these models should look like on the large scale or what they should finally add up to. And to do this, I just want to highlight that it's not just as simple as looking at whether you get the amount of rainfall correctly, but it's also important to understand why you get that amount of rainfall. And so we need process-oriented diagnostics or mechanisms which depict the process through which convection is changing, and that is what this thesis work tries to contribute towards. So thinking about the main, or the two main constraints that are relevant for the type of convective variability that we want to look at today. First one is the weak temperature gradient, where in the tropics they have been observed to show very weak horizontal gradients in temperature, a very small tendency of temperature to change in time. So that you can think of them as tropics as having like a fairly uniform, horizontally uniform temperature profile, which implies that any diabatic heat source in the tropics results in changes in circulation rather than changes in temperature. If I have heating, it is not leading to a change in temperature, rather it will induce circulation which will balance that heat out at the tropics. And the other main constraint is the moisture precipitation coupling, where we have seen that over tropics, precipitation is well correlated with amount of water vapor in the column. And so the more water vapor you have, the more precipitation you can have. And these two constraints kind of together form a moisture precipitation coupling, which governs how large-scale tropical convection can evolve in time. And basically to visualize that, that is where the moist static energy budget comes in. Moist static energy is, you can think of it as a conserved energy quantity, which is conserved not just under upward vertical motion in the atmosphere, but also through condensation processes. And so using the moist static energy budget, which I have here on the right side are the sources and sinks of this energy, left side is time tendency. I can then apply the two kind of like the constraints that I talked about. We have WTG balance, so MSC changes are driven by moisture changes, and then if I use the moisture precipitation coupling, then that says moisture changes represent precipitation changes. So basically, this equation gives you a way to connect changes in rainfall with sources and sinks of moisture or moist static energy. And so it gives you an ability to think about how would rainfall change in time at large scales. And so based on this equation is where we develop, where this GMS phase plane was developed. I'll just ask you to like maybe not think about the GMS part of the definition, but just introducing the phase plane quickly right now. It is formed by taking divergence of dry static energy on x-axis or just any other metric for amount of convection. So you can think of your x-axis as amount of precipitation, And on the y-axis, we put the sources and sinks of moisture or moistatic energy that we saw in the previous equation. And so if those changes, if those sources and sinks of MSE, if they can affect changes in rainfall, then basically whether you have positive or negative on y-axis should dictate whether your precipitation increases or decreases with time. And that is what was observed and shown by previous studies. They showed that on this plot here, points below the black dashed line are the points where the MSE tendency is positive, and those are the points which corresponded with points which tend to increase, which tend to show an increase in rainfall with time, shown by the red color. And vice versa, points above the dashed line are the points where MSE tendency is negative, and those are the points which tend to show a decrease in rainfall with time. And so that kind of re-verifies the simple schematic that we expect from this budget equation, that when, I should stick to this side so that people on Zoom know what I'm pointing at. But so basically, whenever the right-hand side is positive or negative, that can dictate or tell us, it can give us information about whether precipitation will increase or decrease with time. And so, yeah, question.
Sorry, yeah, I just have a question in interpreting the precipitation change in time on the large scale. Would it be, for example, looking at some sort of large scale feature over the full life cycle and seeing how precipitation changes, like the MSE and precipitation change over the full life cycle, perhaps of like a tropical cyclone or something like that? Or is it kind of even on a larger scale than that, or a little bit more of a different?
Yeah, something like that. So like it's representing like a mean precipitation rate over some period. And so if you're thinking of like, say, like an MCS type of system, so if you have one MCS which rains X amount, then the next MCS which comes after that would rain Y amount, and then that Y, whether that Y is greater or less than X, could possibly be represented or be like you can understand that based on this, maybe.
So it's daily average precipitation over 2.5 degree grid boxes, is that right?
Yes, in this case here, this is like a daily precipitation time series which has just been filtered, and so you're basically like looking at changes in daily precip here, but it kind of like more broadly represents like how one MCS system would be different from other MCS.
That makes sense, thanks.
And so basically like the convective variability that I'm trying to describe based on this framework is, probably you have an idea of this already, but it looks something like this counterclockwise evolving orbits on this phase plane. And so this is just showing that in our data we do see this counterclockwise evolution corresponding to the energy budget defining whether precipitation will increase or decrease in time. And this type of variability is what has been termed as convective life cycles, or what we show in our work can also be thought of as moisture recharge discharge cycles. They're one and the same thing. And then this would be like the main focus of our thesis work, is trying to understand this type of variability. Why do we want to do that? That is because our climate models do not do a very good job of representing this type of cyclic evolution in the system. Here is a study which is showing different global climate models, and they're using a slightly different phase space, but it is still equivalent in terms of the type of processes that it represents. And so here, the top panel here shows what you want to expect from observations, but then some models might replicate them very nicely, but other models can be very bad at it. And this is also true in our numerical weather models, in particular at longer lead times. So basically, if you're using your long-term forecast from your model, then at long-term forecast, these type of physical mechanisms are, it seems like somehow they're not being represented that well by the model physics. And so that is why there is a need for more study to understand what is driving this type of variability and what type of processes help drive it. And that brings us to the big picture goal for this work, is to understand this variability, what are the processes driving it, and develop new diagnostics that can be used to carry out such studies and apply to models in the future. So let's look at what are the processes, especially let's look at the sources and sink terms from our budget in more detail and what they actually are. They can broadly be divided into this advection term, which is the first term here, which can further be divided into a vertical and horizontal advection term, and the diabatic flux terms. So we'll look at them one by one. Vertical advection is basically the energy transport by the overturning circulation. When we have convection, we have upward motion, we have convergence and divergence associated with it, and this circulation is then either importing or exporting energy in the column. And what is very important here is that the shape of vertical motion profile is very important to understand whether it imports or exports energy in the column. If we have a bottom-heavy profile shown here, which bottom-heavy implying that the peak upward velocity is somewhere in the lower part of the troposphere, and top-heavy means peak upward velocity is somewhere in the upper part. Depending whether it is bottom-heavy or top-heavy, bottom-heavy would actually add energy in the column. It imports more energy than it is exporting out, whereas top-heavy profile exports more energy out than it is importing in. So it leads to export of energy from the column. And so this is a really important thing to keep in mind. For vertical advection, it is the top heaviness or bottom heaviness of the motion profile, which we would be interested in looking at. Going over to horizontal advection. Horizontal advection is the energy transport by the circulation because of existence of horizontal gradients in MSE, and because of WTG, they are basically coming from water vapor. So although tropics may not show horizontal gradients in temperature, they can have very strong very strong moisture gradients in the horizontal direction, and that can drive this horizontal advection term and impact how things evolve at large scale. The first of the diabatic terms is the column radiation, which represents the grand total of all the radiative fluxes in the column. This includes a number of different processes, including all cloud and water vapor feedback, impact of aerosols, and all the things which are super important and something that we do not understand very well. In fact, impact of clouds and aerosols is considered as one of the largest source of uncertainty in climate models, and that is also, and they also act as a source in sink in this framework here. And the other part is the surface fluxes, which represent the sensible and latent heat fluxes from the surface entering into the column, so they're kind of like a boundary forcing. And overall in observations, what we have seen is that the diabatic fluxes vary linearly with the amount of convection in the column, and so they can be approximated with this with a single line, and that is what the black dashed line in our previous phase plane corresponded to. It corresponded to the regression of the diabatic fluxes to the x-axis. And so basically in the budget, what we are thinking is how each of these terms balance with each other, and basically their interaction, whether they are equal to each other, or if one is more, if there is net import or export, that describes how rainfall would evolve at large scales. And so thinking about on the phase plane what this convective variability corresponds to in terms of real world phenomena. So the way this the phase plane and data on phase plane is set up is that you just take a scatter plot of time series at all locations, and you just make a scatter plot on the phase plane, and that gives you the distribution. So what you are probably seeing are all types of different cyclic modes that we can have in the tropics. They're all kind of being represented together. We are not filtering for any specific time scale, any specific spatial scale. We just apply a simple filter to remove the diurnal time scale variability. And so this phase plane kind of represents the grand total of all the things you're seeing in this animation. And what I want to specify is that you can see waves which are moving across space where they're not changing much, they're maybe not intensifying or decaying, but they're just moving across. These would show up as cycles on the phase plane. If we have a wave which maybe say is not moving, it is stationary, but it amplifies and decays in amplitude, that would also show up as a cyclic orbit on the phase plane. So the phase plane evolution is kind of like has a mix of both of these features here. And so the current GMS phase plane framework presents this mix of variability. Basically, like one of our motivations to look at aggregation was to say like, okay, like I want to look at more at the variability which is amplifying and decaying in time, rather than tune out, filter out the waves which are moving across space. And that led us to think more about aggregation and what framework can we build to look at that. But yeah, I threw out a lot of information. So just trying to put everything together in terms of what are our specific things that we are trying to look at. So for part A with moisture recharge discharge cycles, I'll just present a brief overview of the new diagnostics that we built to study evolution on the GMS phase plane, and why that and what is the importance and how and what are the advantages of using that type of framework. And we'll use that to compare, the evolution of these cycles across different data sets, across different regions. We also have some work looking at whether variability at specific timescales, which we know is driven which has an important role of moisture in it, whether that also looks like this counterclockwise evolution. So is it just a feature which comes up because when you put everything together across different timescales, it shows up as cycles, or are individual timescales also cycles, and do they seem to be consistent with the thing happening at this mixed scale? And part B, in the aggregation chapter, we'll focus on the cyclic variability in terms of changing magnitude of the cycle. So we try to filter out the effect of just waves moving across space. And we present a new phase plane, a modified phase plane, still based on the same assumptions, or the same approximations, but that focuses more on the magnitude part of the cycle. And before I present the results, I'll just quickly discuss the different data sets that we are using. So we have tried to apply these to kind of like show the use of these metrics as valid, as useful diagnostic tools. We've tried applying them to a variety of different data sets. So in chapter 1, I've tried to apply the phase plane metric to field campaign data from Toga and a mix of satellite and ERA interim data. We also compare it with data from an idealized model, where we had an idealized model for where precipitation tendencies depend solely on moisture or precipitation anomalies. So it is driven directly by moisture, and we use results from this simple model and compare them with the observations, whether the simple model can replicate, idea being that can it replicate qualitatively this cyclic feature that we want to see. And then for chapters 2 and 3, we are using ERA5 reanalysis over a longer term time period to look at things. And basically, where I will present results looking at cycles across different domains in the tropics, and we've mainly tried to focus at domains corresponding to 4 major tropical ocean basins. So to say, with the Indian Ocean Basin, Western Pacific, Eastern and Central Pacific, and Atlantic Ocean Basin in the study. Okay, so with that, I'll start talking a little bit about the results and what we tried to do. So starting off with giving a brief overview with recharge-discharge cycles. As mentioned previously, this work is more like an extension to previous work and trying to build on that framework, focusing more on the fact that what is really important for models is getting this counterclockwise evolution correctly. That is where models fail. So to try and look at that, we define a cycles in terms of a phase angle, where we can use the angle to specify the state or the phase of the cycle, And this angle has a physical meaning as well. This angle represents the slope of a line connecting point to the origin, right? And that slope is something that is called as GMS, or the gross moist stability, which represents the efficiency of the cycle in transporting energy. And so, because GMS is a ratio, at shorter time resolution, like say if you're looking at daily time series data, GMS would often become infinite whenever denominator is very small. But this phase angle basically allows you to look at time series of GMS in a finite bound way, rather than having to deal with infinite values. And so, in the interest of time, I'll skip some of this part and basically just present thinking about if we, like how we try to use these phase angles is that to represent the counterclockwise evolution, we compute phase angles and then we compute the time derivatives for these phase angles. So a positive time derivative of an angle would represent a counterclockwise evolution on the phase plane, and so that is in the direction of the counterclockwise orbit. And we use that to plot what we call as phase portraits, where we are plotting the time tendency of the angle on the y-axis and the phase of the cycle on the x-axis. So x-axis is where, at which part of the cycle you are at, and then the time tendency tells you how fast, or like what is the magnitude of that arrow that we were seeing in the previous plots. And so here, shown in green is the total evolution of the cycle. So this corresponds to the green vectors that we saw in the previous plot. And we see the pattern showing the counterclockwise evolution, where tendency is always positive, and it kind of slows down at two regions in the cycle, and it is faster between them. And in black and blue are the contributions to this tendency from vertical and horizontal advection, which shows a similar qualitative pattern to these cycles, showing that advective terms are helping drive this cycle. They help drive and contribute to the evolution, with both vertical and horizontal advection playing a role in this framework. And basically this type of feature can be seen in different data sets. Previous plots which were showing Toga core data. Now if I use satellite and reanalysis data to look at different ocean basins that I showed earlier, I see similar pattern in evolution across the different regions, and in all regions the advective terms tend to have like similar qualitative behavior in the different basins. And the idealized model that I talked about here, we've also compared Toga core observations, and the dotted lines show behavior from that idealized model, showing that the idealized simple model is able to qualitatively recreate the cyclic variability that we expect. And another aspect that I just wanted to highlight really quickly is like these cycles right now, they are more like composite cycles that we're looking at bin mean values. But what happens if we try to look at evolution of an individual cycle? So to try and look at that, what we did is we identified 3 easterly wave events which were observed during a field campaign period, OTREC, and we used ERA5 data corresponding to the same timestamps for these cycles to look whether in our Eastern Pacific box, when we know that an easterly wave is passing through, can we see features of this cyclic evolution on the phase plane? And so I'm plotting a time series for the full box over the phase plane. Different colors here represent the different easterly wave events, and basically the cross symbol for each of the colors is the starting point, and the diamond is the end point. And we see roughly it is not as good or as well behaved as those vector plots, but we see some features of cyclic evolution, particularly like counterclockwise evolution in all 3 cycles, showing that other moisture-driven variability modes also do look like counterclockwise orbits, and that we can also try and, maybe like it needs more work, but we can try and extend this type of framework to look at individual events as well, rather than looking at aggregate or like composite cycles. And so So these are just like some key conclusions that I talked about. Main being that advective terms are the main drivers behind these cycles. Both vertical and horizontal advection can contribute to it, and role of moisture is really critical to recreating this type of variability. And so with that, just having that in mind, I'll now talk about, maybe switch gears a little bit and talk about aggregation, disaggregation cycles. And here basically the idea is that convection, especially large scale organized convection, has large impacts on the environment. But one of them being that it can redistribute moisture or MSC in the domain. So for our process-oriented diagnostic, rather than look at the process, can we also just try and visualize convection in terms of its impact on the environment? Can we make a metric to look at evolution of convection in terms of how it is impacting the environment? And so that brings us to these cycles. So I'll present the MSC variance budget, which allows us to do that. And we build a MSC variance phase plane, surprise, surprise. And we look at what type of this cyclic variability is seen on this new phase plane, and what are the processes that contribute towards that. So looking at these convective aggregation, disaggregation cycles, by aggregation, visually we are thinking of clumping together of convection or clouds. This term maybe is motivated from convective self-aggregation, where in idealized modeling studies with uniform boundary conditions, it was observed that convection can still aggregate without any external forcing, but still tends to aggregate with time. And so this represents that there are very inherent and implicit ways in which convection can organize itself, and this is called self-aggregation because it is doing this in the absence of boundary forcing. And when we come to the real world, you have these mechanisms, plus on top of that you add on any type of boundary conditions that you'll have in your real atmosphere, and that gives you aggregation, which is not necessarily self-aggregation, but could be. And you want to understand how self-aggregation can be important for aggregation in the real world. Some previous studies have tried to show that these mechanisms are important for specific real-world phenomena, but more importantly, what self-aggregation studies highlighted and has been shown also for aggregation is that this type of organization of convection has huge impacts on the environment. It makes the domain drier on average. It reduces high cloud cover, and what that allows is it allows the domain to emit more outgoing long wave radiation as it gets more aggregated. And so it is really important for how sensitive our domain or our climate can be. Particularly, for example, if with climate change, with the rising sea surface temperatures, if, for example, aggregation increases, then that would imply that with increased aggregation, you can have higher long wave, outgoing long wave radiation, which would correspond to our temperatures, our surface being more efficient at cooling down, basically. So the temperature would increase at a slower rate. So it's really important to understand climate sensitivity and what this clumping together and the other big impact on the domain that it has is the redistribution of MSC or moisture in the domain, which leads to increased spatial variance. And so what we want to try and understand is what is the nature of aggregation in the real world, how can we leverage the rich literature that we have from idealized models to this literature by connecting these two. And to do that, we try and come up with a common framework that is motivated from the framework used in idealized studies and applying it to observations. And we use that to understand the cyclic variability in the real world. And the other main hypothesis that we are thinking about, especially motivated by results from previous section, is that we expect advection to be the main driver of such large-scale convective variability based on MSC budgets. So let me introduce the MSC variance budget. So MSc variance budget is based on the idea that with time, convection in a domain, if it is like uniformly distributed across the domain, with time, it will clump together. And this also corresponds to creation of very moist columns and very dry columns. So if I'm computing a spatial variance, a variance with respect to the domain mean of MSc, I will see an increase in variance value with aggregation because I have a bimodal distribution rather than a Gaussian distribution now. And so we can use spatial variance of MSc as a metric to represent how much aggregation we have in the model. And when we try to compute the spatial variance of MSc in the domains, we see that we can actually use that as a metric. It looks like an aggregated thing here. I'm showing for the 4 ocean basins, I'm showing the spatial anomaly of moistatic energy. In top panel, when our total domain variance is small, that is when it is least aggregated, and in the bottom panel, when it is more aggregated. And we see that when things are more aggregated as per this spatial variance metric, the domain does look more aggregated in the sense that it has a well-defined moist region and a prominent dry region. There is sharp gradients across them, and there's a sharp boundary. And when things are less aggregated, things seem to be more uniformly distributed across the domain. They are still aggregated to some extent. They're not completely disaggregated, but the extent of aggregation is less. And so if we have a budget, just like the MSc budget, that gives us the sources and sinks of this variance, then we can make the same type of arguments to understand what drives changes in aggregation. And so using the MSc variance budget, we can look how the radiative, surface flux, and advection terms are contributing to this variance of MSc rather than just that. And here, basically, in this budget term, a positive term would basically represent a positive feedback for aggregation, which basically corresponds to, like, for example, say if you have a moist column, which is already moist in the domain, if the budget term tends to add MSc to that column, then it is a positive feedback because it tends to make the moist column moister. Or conversely, if something makes a dry column drier, then that would be a positive feedback and have a positive variance value in the budget. And a negative budget term would imply a negative feedback for aggregation. And to look at the evolution of this variance metric, we can create the phase space using similar framework, where we can plot the amount of aggregation on the x-axis. So that is spatial variance of MSc. And then on the y-axis, we plot the time tendency of variance, whether things are aggregating or disaggregating in time. And so on this phase plane, an aggregating process should look something like this, and a disaggregating process should be the opposite, in the opposite direction, completing that cycle. And so basically, if you have evolution of increasing and decreasing aggregation, that shows up as clockwise evolution in this case on this phase plane. And if we try and create similar vector plots to the previous studies, looking at reanalysis data in the different ocean basins, and looking at bin mean evolution on this phase space, we see that it very nicely kind of verifies the idealized picture that we expect from the budget. And we can look at the contribution to this cycle from the different budget terms in terms of whether they are a positive or negative feedback, and how that varies as the domain is getting more aggregated or less aggregated by plotting contours for each of the budget terms here. And here, basically starting with column radiation, we see that it is always a positive feedback. That means it tends to make moist columns moister. And we see that as domain gets more aggregated, as you move right on the x-axis, it is becoming a stronger positive feedback. And this is very well expected from other studies, where with higher, with stronger convection, you expect there to be more deep clouds, which warm the moist columns, which make them moister. This is very consistent with that. For surface fluxes, we see that they act as a negative feedback throughout the different phases of the cycle, and that they become stronger negative feedback as things get more aggregated. And this most likely represents that in the dry regions of our domain, we have higher disequilibrium between the surface and the atmosphere, which is driving stronger surface fluxes, which add moisture through latent heat energy in the dry columns, acting to moisten the dry columns and hence behaving as a negative feedback. And we see that for vertical and horizontal advection, they can behave as both positive and negative feedbacks during different phases. But overall, we see that vertical advection becomes a stronger positive feedback as things get more aggregated, and horizontal advection tends to become a more negative feedback as things get more aggregated. And we'll look at this in more details in subsequent parts of the presentation. But yeah, so to look at this in more detail, we can also try and represent this through, we can also like this is showing evolution across different phases of the cycle. We can combine all the different phases by projecting our MSc budget term onto the tendency of MSc variance, which represents contribution to propagation of the cycle. So what we are doing here is that we take our budget term in X, we project it onto MSc variance tendency, which is our y-axis, and so we are looking at whether when tendency is positive, is the budget term also contributing in a positive way or not. And so this shows whether your budget term can co-vary with the y-axis. So for example, for horizontal advection here, we see that horizontal advection changes with the y-axis. As y-axis increases, horizontal advection is also changing positively. It is increasing in magnitude. And so you would expect a positive contribution to propagation from horizontal advection. And to look at how well do these terms behave or contribute towards maintenance of the cycle, that is, when you have when your domain is already aggregated, whether the term tends to keep it in that aggregated state or does it try to contribute in a way which removes that aggregated state. We do that by projecting onto the MSc variance or the x-axis in this case, and we are looking at how things vary with the x-axis, where we see that as domain gets more aggregated, the MSc budget term is becoming more negative, and so that should show up as a negative feedback in this maintenance term. And so just putting this all together for the different terms and looking at all the different ocean basins, looking at the propagation plot here first, we see that almost all of the propagation is coming from horizontal advection. This shows that horizontal advection is really important to understand whether things will aggregate or disaggregate with time in terms of driving or changing these cycles. And in terms of understanding what is the extent to which it will aggregate or disaggregate, that is given by the maintenance terms, that is given by contribution to maintenance terms in the top panel. And there we see that all the four terms contribute significantly, with vertical advection and column radiation being positive contributors to maintenance, and horizontal advection and surface fluxes being negative contributors. Just summarizing what I presented here, we're expecting vertical advection and column radiation to act to maintain the existing variance anomaly. So if you're more aggregated, vertical advection and column radiation behave to keep it aggregated. Horizontal advection surface fluxes tend to try and disaggregate it. But overall, whether the system aggregates or disaggregates, that is well correlated, and it is indicated by whether horizontal advection is aggregating or disaggregate, contributes to aggregate or disaggregate things. And so, the focus in terms of understanding how these different terms vary, in the idealized models looking at self-aggregation, they have found the diabatic fluxes, particularly column radiation, to be very, very important, and expect that to be the key player in defining this relationship, mainly for maintaining aggregation. And so in this study, where we are seeing this signal from the advection terms in driving the growth of these cycles, we want to further look at what are the exact changes in the profiles of horizontal and vertical circulation that can help explain these type of characteristics. And so we'll try looking at that both for horizontal and vertical circulation, where first we'll start with changes in vertical circulation here. So here I'm trying to now connect back the MSc variance budget with MSc budget. So rather than looking at variance contribution from advection, we are now going back to what does vertical advection do in the MSc budget, and we can look at that by defining and organizing our domain into column MSc percentile bins. So this is, you rank columns from driest to moistest, and you put them on the x-axis where lesser values are dry columns, higher values are moist columns. And then on the y-axis, I have the average column advection, average column vertical advection. And so what this is showing is that negative values in the moist column shows that moist columns export energy out. And the dry columns, at least when things are less aggregated, the dry columns shown by the orange line have a positive vertical advection, that is, they are importing energy. So moist column, so vertical advection is redistributing MSc in the domain where it is taking MSc from moist columns and taking it to dry columns. But as things aggregate, as we shift from this orange line to this blue line, we see that moist columns still tend to get dried up because of vertical advection, but things change and the dry columns can also become a little bit more drier, and so that would imply that dry columns tend to get moister if the domain is more aggregated from vertical advection. And we can also represent this in terms of as a difference between the most and least aggregated state. So on the figure on the right here, in the black line shows basically the difference between orange and blue line on the left. And so that is showing that with aggregation, moist columns are exporting more energy out of the column, but dry columns are also tend to export more energy out, and it is kind of going into the middle columns somewhere. And the other lines on this plot actually correspond to a decomposition of the vertical advection term, where we want to try and understand, okay, this change of dry columns tending to get drier and moist columns tending to get drier as well, whether these changes, are they coming from changes in vertical motion profile, or are they coming from changes in this DHDP term, which is our moist static energy profile. And so to do that, we do this decomposition where the bar denotes average profile between the most, across the most and least aggregated cases, and the subscript A denotes the anomalies from this mean profile. And so here in the plots, as we see in all the different ocean basins, the green line corresponds very well with the black line, which is the total term, and this green line corresponds to the third term, which shows action of anomalous or changes in vertical motion profile on the main MSc state. And so this represents that changes in vertical motion profile can help us explain how vertical advection changes. And we see that across the different ocean basins, we see a consistent signal in dry columns showing a tendency to dry up from vertical advection consistently in all four basins, whereas if we look at the moist columns, we can have the Indian Ocean and Eastern Pacific, where moist columns tend to get drier, but in Western Pacific and Atlantic Ocean, moist columns tend to get moistened up. So why does that happen? And this is all happening because of vertical motion profile changes. So to do that, we plot the profiles of vertical motion. Here in these plots, I'm showing the vertical motion profile in the contours, and shading is the MSE profile. In the left panel is the mean state, so it has the mean omega and mean DHTP. So it shows mean ascent in the moist columns, mean descent in the dry columns. So the thick solid line is the zero contour, and we see that dry columns are drier, moist columns are moister. And then the other two panels on the right show the composites for the most and least aggregated state, and these show the anomalies. So the contours are anomalous vertical motion profiles. And so what we see is that when things are more aggregated over the dry regions, we see an enhancement, we see a positive anomaly in the low levels. So that is an increased increased downward vertical motion in the dry columns, and we see enhanced upward motion in the moist columns. And basically this low-level subsidence relates to what I talked about initially with the vertical motion profile shape, and in terms of the top heaviness or bottom heaviness being really important for how the advection term contributes to the MSE budget, where in this case, bottom heavy subsidence can contribute to the drying of the dry column. And for the moist columns, from these profiles, like it looks like a very like balanced profile.
Sorry, Vijit, can you just clarify what the colors and the contours are? I don't think you ever said that.
Yeah, so the colors, the shading here just represents the MSE profile here. So again, in the left panel, it is the mean MSE profile, and on the right panel, it is the anomaly from the mean MSE profile, showing that more aggregated cases show a more stronger, like they're characterized by this decrease in MSE in the dry columns. So basically, if you're thinking of a less aggregated versus more aggregated state, the signal is that more aggregated state has stronger dry regions,
And the contours are the vertical motions.
yes, and contours are the anomalous vertical motions here, and so yeah, so
Dan?
Yeah, so can you clarify the contours of the anomalous vertical motions during the more aggregated and least aggregated states?
yes, they're composite for the and the thick solid contour is the zero line. I realized
Oh, okay, I see. Never mind, got it.
yeah, and they have similar shape because
They're just
because
opposites.
by construction
Got it.
and
I didn't see
showing.
the minus sign. I was trying to figure out why that was the case. Sorry.
Same issue.
Yeah.
Yeah, sorry about that. I think they could have made the figure a little bit
Wait,
better.
where is there a minus sign?
There's the flip flop.
The contours, yeah,
have
they-
opposite polarity.
Yeah, like they are negative here, positive here.
Yeah, sorry.
And they're the anomalies from each other, not from.
Anomalies from the mean.
Oh.
These are anomalies from the mean. Yeah, so basically, like what this is showing is, like I'm presenting results here only for the Indian Ocean, but we are seeing a consistent increase in low-level subsidence. As the domain gets more aggregated, we see an enhancement in upward motion in the moist columns. And if we try to compare what is happening in the driest and the moistest columns in all four ocean basins with aggregation, I try plotting them here, where left panel shows the vertical velocity profile changes in the dry columns. Now the anomalies are shown as a difference between the most and least aggregated state, just to enhance the signal more. But basically, what this is also showing is the enhanced low-level subsidence, and that all ocean basins show the enhancement in low-level subsidence. Whereas if we look at the moist columns, we see that upward motion gets enhanced in all the columns, but the shape of the enhanced vertical motion profile is different in the different ocean basins. In Indian Ocean and Eastern Pacific, the shape is more balanced, it is more consistent, it has this overall middle heavy shape, so to say, which corresponds to the moist columns getting drier in the previous plots that we saw. But in Western Pacific and Atlantic Ocean, what we see is that vertical motion gets enhanced in a more bottom heavy fashion. And so a more bottom heavy upward vertical motion can help import moisture in the column. And so in those two basins, we see moist columns getting moister.
And it's not that the columns are getting moister, it's that the tendency is changing.
Yeah, the
tendency
contribution
is
from vertical advection in those columns, they tend to get moisture because of vertical advection and changes in vertical profiles. And so basically, this shows a difference between like these two feedbacks where changes in the dry regions represent a positive feedback on aggregation, which is tending to dry the dry columns, so it's a positive feedback. Whereas in moist columns in different basins, you can either have a positive feedback from advection if it dries the moist columns, or you can also see a negative feedback in the different basins if it tends to moisten the moist columns. And this relates, and if we go back and relate this to the overall plot that we see here, we see that when we combine both the most and least aggregated state and look at the full cycle, we see that vertical advection tends to behave in a positive feedback way. So it seems that changes over the dry regions are dominating over what is happening in the moist columns in a net state. And so the last thing I'll be presenting today are the changes in the horizontal circulation and how the horizontal winds change with aggregation. So here I'm presenting a projection of the horizontal wind vector along the MSE gradient. So I'm trying to look at how much of the horizontal wind is going up gradient in MSE. And so if I have columns tagged from dry to moist, positive values of this projection indicate that flow is from dry to moist columns, that is to the right on the x-axis, and negative values show that it is to the left from moist to dry columns. And we see that when the domain is least aggregated or less aggregated, the horizontal flow near the surface tends to be from moist to dry columns. But when things are more aggregated, the flow reverses, like the circulation normally changes sign, and it is now from dry to moist columns. And so there is this reversal in horizontal winds between the most and least aggregated states. And we think this is potentially consistent with some other work looking at how Hadley cell interacts with eddies in the tropics, where basically the simple schematic shown in this paper, in this recent paper by Adamis and Maithel, show that if we have a strong Hadley cell in the tropics, and if we expect it to be driven by or shown by existence of strong MSE gradients again are the more aggregated state, then that strong aggregated state can drive or support is unstable, and it can create and intensify moisture eddies, which tend to go from the moist columns to the dry columns and help in redistributing the energy, leading to a less aggregated state, and it can eat up the gradients in the Hadley cell, and as the gradients get eaten up, Hadley cell is no longer strong, there are no longer strong gradients in the domain, the eddies weaken, and then things can again start aggregating back up, and the flow would be anomalous, would be opposite of this moist to dry column flow, which we are seeing in our observations. So that could be a potential hypothesis of why horizontal advection or horizontal circulation is changing in the way that we are observing it to change, and how horizontal advection could help in driving these aggregation disaggregation cycles by basically feeding on the existing MSE gradient and redistributing it. And so in terms of thinking back about what this aggregation looks like, as we saw in the spatial anomaly plot, we were seeing bands of high MSE and low MSE, and things were more aggregated, and basically a disaggregated state is weakening of those gradients where MSE gets redistributed. And in this kind of setup, the important thing would be that aggregation is at these scales, aggregation is defining the extent or energy of the Hadley cell, and the eddies themselves, which are also moisture modes, they are not instances of aggregation as such at these large spatial scales, but rather they are a disaggregating process in these scales. And so to just try and like wrap up and conclude in a couple of minutes here. So for the aggregation disaggregation cycles, the main thing that I want to highlight is that we saw that column radiation and surface fluxes are strong contributors to maintenance of aggregation. However, it is the advection terms which are more important to understand whether things will aggregate or disaggregate in observations. And in terms of horizontal circulation, like in terms of circulation changes, we see that with more aggregation in observations, we are seeing an increase in low-level subsidence, which can drive MSE out of the dry columns, helping maintain the aggregation, and we see that more consistently across the different ocean basins. And we see that horizontal circulation goes from moist to dry columns when the domain is less aggregated. So just overall conclusions, thinking of the two main goals, the broad picture goals that I outlined for this thesis work. Think about what are the characteristics of the convective variability that is driven within the confines of the two physical constraints that I introduced. And that is that at these scales, within those confines, this moisture-driven variability, it exhibits clockwise, it exhibits cyclic evolution on this GMS or MSE variance phase plane. It is counterclockwise on the GMS phase plane. And that the evolution or these cycles are mainly seem to be driven by how the circulation is transporting energy with it. So they're driven by the advection terms. And these can be seen at a range of different scales in different regions with common features across these different regions. So there is something, so these represent very inherent mechanisms in which convection organizes itself, and it makes it even more important that our models can replicate this behavior more accurately than what they do right now. And in terms of contributing towards what are the new diagnostics that we are proposing, we are presenting two main diagnostic frameworks. One is the phase angle framework, which allows us to look at more to look at evolution of convection, especially that GMS quantity at shorter time resolution, so like in a daily time series data, which was not that easy before. And using the MSE variance phase space, we are able to visualize convection and characterize convection in terms of its impact on the large scale environment. This allows us to compare results with idealized studies showing self-aggregation, or just looking at the evolution of the environment with respect to convection. And with that, I'll quickly acknowledge a lot of people. Maybe not all of them are here on the slides. I would like to acknowledge my advisor, Professor Larissa Back, for giving me this opportunity, funding, her mentorship, advice, and everything else during the past 6 years. My committee members, Professor Adames, Professor Henderson, Professor Valmont, Professor Liquid, and Professor Steckman for their contribution and mentorship. I would also like to acknowledge Professors Seshadri and Professor Srinivasan in India, who I kind of lugged into getting an opportunity to work in atmospheric science with them, which was my introduction to the field, and that motivated me to apply for grad school in the first place. Without that, I would probably not even have thought that something like this field exists. I didn't just meet people who work on atmospheric science before then. So a huge shout out to them. I would also like to acknowledge all our group members, both past and present. Puni, I think he did the Ph.D. thesis part 1. This Ph.D. would probably be part 2 of that. Zach, who I overlapped with for a couple of years while he was here. Miguel, who has been my academic twin in my journey here, and twin who we are kind of leaving him alone and going. So yeah, not so great for him, I guess. But yeah, hopefully he's enjoyed the 1 year. It has been nice having him, having a new face in the group, and new ideas. I would also like to acknowledge all the people in UAS, all the faculty members, Pete, all the grad students and staff members for their help throughout the years. Most importantly, I would like to thank my parents for their support, for everything. They have literally been supporting me throughout all this. They were literally here for 1 month and helping me through the writing phase, like giving me, like I don't have to worry about anything else, just sit and write, don't focus on anything else. So they have really brought me here, or like at least like making it possible that I defend today and not later. And all my friends here in Madison, back in India, for all their support, emotional support through the different phases, ups and downs of the Ph.D. And with that, I'll take any questions. Thank you. Yeah, John.
You showed some nice distinctions between the ocean basins, East Atlantic or Eastern Pacific. Is that fully understood at this point, or not?
Not fully. So I think like I'm showing some features in variations in terms of this phase plane framework, but I guess like these are motivated from the changes in vertical motion profile shape variabilities, particularly between Western and Eastern Pacific, which I think like that was like part of Larissa's thesis work, which kind of showed that. And we are still investigating what exactly control like makes vertical motion profile bottom or top heavy in the different basins. That is an active area of research. My other lab in Miguel, his thesis work is on that. And they're coming up with combining these ideas that it looks like it's a combination of dynamics coming from sea surface temperature gradients with the thermodynamics, with how the emissive profile is, which leads to these changes.
And as a follow-up, I would just ask, you seem to focus strictly on the tropical waveguide, or the tropical zone. What about monsoons?
Yeah, that becomes tricky. So like, yeah, we do not try to extend beyond this like the waveguide region, as you said. With monsoons, especially like if you're looking at monsoons over land, that becomes an entirely different case, because then you have all the external forcing coming from land. If you're thinking of monsoon systems over the ocean, I think like to some extent with the aggregation disaggregation boxes in terms of the ITCZ band moving up and down, it can represent some of those dynamics, but not completely, because it is not structured in that way. Juliet.
Yeah, I think I kind of have a follow-up to John's question, because your question was a question that I had. But, so I'm wondering if when you're talking about the changes in the vertical motion profile being a large influence on the change in the vertical ejection component, is it essentially just the differences between the top heavy and the bottom heavy vertical motion profile, or is it the tendency or the change in the vertical motion with time? And if it's that case, what could be contributing to the change in the vertical motion profile, like the tendency to?
Like we expect that they are driven more by changes in vertical motion profile shape. Like that is what is more important. Like with time, if you have like more vertical motion or less vertical motion, like if you normalize it by amount of convection, it will still be the same. Right? So like thinking of in terms of that is like the use of GMS, that it makes you think about like a normalized quantity. So even if convection increases with time, like vertical motion increases with time, amount of convection would increase, so you have the same efficiency. But what we are seeing in terms of the cyclic variability is that there's also evolution there's also like this change in efficiency, and that change is dictated by vertical motion profile shape changes rather than just amount of vertical motion itself. Does that answer? Is that what you were getting at?
Yeah, and the vertical motion profile shape changes, is that if I can imagine, is it like changes in space or changes in time? I guess if that makes, yeah. Like, so if I'm just looking at the West Pacific,
Changes in time.
it's, okay.
Yeah, that would be changes in time, and like in particular, think about at these large scales, it basically represents like, say if you have like two NCS systems, again to go back to the same example, the first NCS system could spend more time in the growing phase or like the bottom heavy phase of the NCS.
Yeah.
That would be like the bottom heavy large scale, and the top heavy large scale would be the next NCS spending more time in the mature stage, like the stratiform convection stage, where it stays with the top heavy profile for a longer time during its life cycle. And so on the large scale it shows up as top heavy, something like that.
Great, thank you.
Srinath.
So do you expect some kind of balance between like the vertical and horizontal advections because like due to continuity or something, or is it, or would you like classify them as fairly separate physical processes? Like I was thinking whether you can think of them as the same physical process, but you have separate budget terms for both of them also, right? So
Yeah. No, that's a very good question, and something that has also thrown me around in loops a lot of time. And I guess like my understanding or like my current viewpoint on that is that they are related to some extent, and this is mainly based on the fact that we are able to see a consistent signal from horizontal advection in different ocean basins. So like between vertical and horizontal advection can be driven by external factors like SST gradients and things like that, which create the horizontal gradients. But the fact that you can see a close phase relationship between convection and horizontal advection in different environments suggests that there is some way in which horizontal advection is being or like is in balance with the amount of convection you have. So like amount of vertical motion that you have that is able to dictate or create or govern how horizontal advection also behaves in this scenario. And so I think they are related in some way. How exactly they are related, I don't know, and it needs more work, and would be actually like an important piece in the puzzle to understand how convection is able to organize itself in this similar fashion across different regions.
You kind of expect them to be somewhat related through the divergent circulation, and then less when it comes to the rotational circulation. So the divergent circulation, you have some vertical motion somewhere, and then that's associated with horizontal advection to the edges of the wingers. Vijit knows that too. We went around a lot what to write about this horizontal advection versus vertical advection question in this paper that we have. We kind of thought future piece of work might be to try and split things up into a divergent circulation and a rotational circulation and do some of these same diagnostics. Or the horizontal advection associated with the divergent circulation versus the horizontal advection associated with the rotational circulation.
Any other questions?
Sorry, I have one.
Yeah.
Final. So in the West Pacific, you were showing that there was a little bit more of a like bottom heavy profile in the moist column, and that it would continue to moisten. And I think from your previous work, the West Pacific is generally like produce top heavy profiles. So how does that connect to, like, how does what you're showing connect to what we generally know about vertical motion profiles?
I guess I didn't have the.
Want to pull up the plot? Because I don't remember what it looked like.
Yeah, no, I don't.
Yeah, that plot.
Yeah.
Next plot. That plot.
Yeah, so basically like Indian Ocean is in
So-
blue, and Western Pacific has this more bottom heavy structure, but yeah, I guess I don't have, like if I look at the full profile, like here for the Western Pacific, you do see that Western Pacific is more top heavy, and because these are anomalies from the mean profile,
Yeah.
so like you'll expect some structure like a top heavy contour like this in the mean, and the deviation from that mean would have like a bottom heavy structure. So it is still overall top heavy, consistent with previous studies.
So more aggregation is associated with making it a little bit more bottom heavy.
Interesting. Oh, that's really interesting.
Don't know why. Maybe stronger SST gradients are associated with more aggregation. We focused on what was the same between the ocean basins rather than trying to understand just time constraints, trying to understand all the differences and hypotheses about why they might be there.
I think there are no questions on Zoom as well.
Any final questions from non-committee members? Committee members will get their chance in a couple minutes. Okay, well, let's thank Vijit again.